Sending data across the internet is a constant battle against interception and theft. But the mathematical layers protecting us aren't magic. They are just highly specialized tools. In this episode, we are breaking down the core fundamentals of modern cryptography. You'll learn how hashing, symmetric algorithms, and public keys actually work together to secure the digital world.
Early cryptography relied on obscuring text through mechanical patterns. The bifid cipher worked by mapping letters to numbers across a grid, while the Playfair cipher scrambled messages using a 5x5 matrix of non-repeating characters. Those ciphers failed because human language is predictable. Attackers used frequency analysis to identify common letters, or applied the Kossiski examination to track repeating letter intervals and break complex Vigenère ciphers. Today, networks transmit gigabytes of streaming video, banking records, and Bitcoin ledgers. Text scrambling puzzles cannot secure this volume. Modern digital security relies on operations that are computationally infeasible to reverse, relying on the unique properties of prime numbers and modulo operators. This diagram illustrates modulo math, often called clock math. It calculates the remainder after division. For example, 29 modulo 12 equals 5. These repeating mathematical loops make it easy for computers to calculate a direction forward, but mathematically difficult for an attacker to determine the starting point. To secure a digital world, we deploy an entire toolkit of specialized mathematical algorithms, each designed to stop a specific threat: data theft, alteration, or impersonation. The first tool is hashing. This is a one-way mathematical function used to securely store passwords and mathematically prove that a file has not been altered in transit. Hashing relies on the avalanche effect. Changing the first character of an input file results in an entirely different hash output, instantly exposing any tampering. Older hash formats, like the 14-character LM hash, are fragile and easily broken. Systems upgraded to 128-bit MD5 hashes, eventually establishing the modern NTLM standard used by Windows to protect credentials. Attackers target these hashed passwords using three main methods. Dictionary attacks systematically test common words. Brute force attacks test every character combination. Rainbow table attacks map hashes against massive pre-compiled lists. By verifying that the message received is identical to the one sent, hashing provides the mathematical proof required for data integrity, ensuring that your information hasn't been secretly altered. While hashing verifies data, symmetric encryption secures it. Because both parties know the algorithm and share the exact same key, this method operates at incredibly high speeds, making it ideal for encrypting large volumes of data. Symmetric algorithms use two approaches: stream ciphers, like CompTIA or the highly vulnerable RC4 cipher used in early 40-bit web networks, encrypt data bit by bit. Block ciphers, meanwhile, process data chopped into rigid, uniform blocks. Standards dictate block cipher strength. Skipjack uses an 80-bit key on a 64-bit block. DES uses a 56-bit key. The current gold standard is AES, which forces data through 10 mathematical transformation rounds for a 128-bit key, and 12 rounds for a 192-bit key. But processing structure matters. If you use electronic codebook, or ECB mode, identical plain text blocks will always produce the exact same ciphertext. This reveals visual patterns in the underlying data, exposing it to attackers. The solution is cipher block chaining. CBC applies a random initialization vector to the first block, then change the scrambled result into the next block. To further protect the data, an output feedback loop mitigates copy and paste attacks by feeding the ciphertext back into the system. Symmetric encryption is the raw muscle of cryptography, executing the heavy lifting required to lock down massive datasets in real time. A logistical problem limits symmetric encryption. How did two employees securely share their single secret key over a public network without a bad actor intercepting it? Asymmetric encryption solves the delivery problem using two distinct keys. The sender encrypts the symmetric key using the recipient's widely distributed public key. Once locked, the data can only be decrypted by the recipient's unique private key. Businesses scale this identity verification using public key infrastructure, or PKI. A trusted certificate authority issues digital certificates to organizations, signing it with the root CA's private key to mathematically prove the company is legitimate. Administrators verify these certificates by checking their unique SHA-1 thumbprint. They export the certificate and its chain of trust using the PKCS 12 standard and perform key recovery operations strictly during the certificate's active issued phase. Together, asymmetric encryption and PKI function as a digital passport system. They guarantee you securely hand symmetric keys to verified entities, keeping imposters out. These cryptographic layers combine to secure physical network infrastructure. Early Wi-Fi security evolved from WEP to WPA by deploying a 128-bit RC4 cipher. The TKIP protocol patched early flaws by hashing the initialization vector and the secret key, paving the way for WPA Enterprise, which enforces access through a dedicated authentication server. For remote workers, corporate VPNs utilize IPsec to establish secure tunnels. They execute the key exchange over UDP port 500. None secure the payload using Protocol 51, the authentication header, and encapsulating security payload, allowing intrusion detection systems to inspect traffic at both endpoints. Establishing these connections requires caution. Basic Diffie-Hellman key exchanges are highly vulnerable to man-in-the-middle attacks if an adversary intercepts the initial handshake. Upgrading the exchange to elliptic curve Diffie-Hellman provides perfect forward secrecy. By generating temporary keys for every connection, it ensures that even if a long-term master key is compromised, past session keys remain completely safe. Network security operates as an endless arms race, continuously layering new cryptographic protocols to patch vulnerabilities the moment attackers discover them. The Bitcoin peer-to-peer network serves as a case study for how these individual tools can be synthesized into a larger system. Individual wallets and transactions on this network are signed and secured using a 256-bit private key, utilizing the same asymmetric delivery principles that protect corporate networks. The integrity of the ledger is maintained through hashing, which chains every block together. Because adding new blocks is deliberately computationally expensive, the system creates a mathematical disincentive for anyone trying to rewrite the transaction history. This synthesis of symmetric muscle, asymmetric identity, and hashing integrity creates an interconnected mathematical ecosystem. By layering these tools, we move past simple padlocks and into a framework that allows our entire connected world to exist safely.
That's the breakdown for this session. If this guide helped untangle the concepts, hit subscribe so you don't miss our next deep dive. To help you study, we've already built the flashcards and notes for this episode. You can study them directly from the link in the description. Thanks for tracking with Kernel Panic Logs. Stay secure, and we'll catch you in the next one.